Welcome to this explainer. Today, we're diving straight into the engineering of pressure vessel heads. You know those massive steel cylinders you see at industrial plants? They're holding extreme volatile forces. The real question is, how do we keep all that pressure safely locked inside without blowing the ends right off? Let's get into it. Think about a giant metal soda can. But instead of fizzy water, it's packed with explosive pressure at a massive industrial scale. How do you permanently seal the ends of a cylinder like that so it doesn't suddenly launch into the stratosphere like a rocket? You definitely can't just weld a flat plate to the end and hope for the best. The internal forces would rip it right off. That's where a highly engineered component, known simply as the head, comes into play. While the straight, cylindrical part of the vessel, the shell, distributes forces pretty evenly, the physics at the ends get incredibly complex. The head is the capstone. It has to bear immense physical force and keep the whole system intact. It is, quite literally, the crown of the pressure vessel. To pull this off, engineers have developed a whole catalog of head geometries over the decades. We're talking everything from completely spherical caps to flatter dished shapes and even entirely flat discs. Why so many varieties? Well, the exact shape completely dictates how pressure is distributed across the metal. Now, a perfect sphere is technically the strongest, but it takes up a massive amount of vertical space and is super expensive to make. So engineers are constantly balancing strength, space, and cost. Out of all those options, though, there's one undisputed champion. It's the absolute go-to standard for the vast majority of vessels out there because it hits that perfect sweet spot between structural integrity and manufacturing efficiency. We call it the 2-to-1 ellipsoidal head. The anatomy of this ellipsoidal head is actually really fascinating. It breaks down into two distinct zones that you absolutely have to understand. The top, relatively flat section is the crown, and that sharply curved corner where it sweeps down to meet the straight shell, that's the knuckle. Knowing the difference between these two is literally the key to vessel safety. Before we look closer at those zones, here's a brilliant little mathematical constant the industry relies on. The height of this standard head is always exactly 1/4 of the vessel's total inner diameter. We call it d/4. So if your vessel is 4 meters wide, the head is exactly 1 meter tall. Every mechanical engineer uses this constant because it makes calculating volume, clearances, and weight incredibly fast and precise, no matter the scale of the project. Okay, let's compare those two zones. The crown area is a gentle, sweeping curve. Because the bending is so gradual, it naturally has very low residual stress for manufacturing. It's stable. But the knuckle? Completely different story. To connect the crown to the vertical shell, thick steel has to be bent incredibly tightly at a very specific radius, exactly 0.1727 times the diameter to be precise. That is a punishing bend, and it traps a massive amount of stress right in that corner. Let's talk about what residual stress actually means here. When you force extremely thick industrial steel plate to bend that sharply, you create a serious mechanical conflict. Even after the manufacturing presses let go, the microscopic grains inside the metal are still pushing and pulling against each other. They desperately want to spring back to being flat. Those are hidden, trapped forces, permanently locked inside the material. A great way to visualize this is what we can call the paperclip effect. If you take a standard metal paperclip and bend it back and forth a few times, what happens? The corner gets super stiff, it gets noticeably hot, and eventually it becomes brittle and just snaps. That stiffness and brittleness, that's the exact same dangerous residual stress we're talking about, just scaled up to massive industrial proportions right in the vessel's knuckle. Because of that invisible tension, there are incredibly strict, non-negotiable rules for the knuckle zone. It is an absolute danger area. You never install nozzles or pipes there. You do not weld structural attachments like ladders or platforms to it. The overarching goal is zero structural discontinuities, which is really just a fancy engineering term for do not interrupt the metal. No holes, no heavy welds, period. Why are holes so catastrophic here? Because they create local stress. If you cut into a knuckle that's already stretched to its absolute limit, you create a massive spike in tension focused right at the edge of that cut. The metal is already fighting itself. Adding a geometric hole acts exactly like a microscopic crack, just waiting to tear the entire thing apart under pressure. But here's the kicker. Even if you follow all the rules and don't cut any holes whatsoever, the sheer stretching from forming that curve in the factory leaves the metal dangerously tense. Before this vessel can safely hold anything like volatile chemicals or high-pressure steam, we have to find a way to relax the metal. So how do engineers fix it? Well, global standards dictate a strict heat treatment process. Once carbon steel goes past a certain bending threshold, meaning really high elongation, it requires what's called post-weld heat treatment. They literally take this entire massive steel head and bake it in a gargantuan high-temperature oven. That intense heat safely relaxes the steel's molecular structure. Those angry, stretched grains settle down, and all that trapped residual stress is completely neutralized. It all comes down to a simple truth in vessel engineering. The smallest curves prevent the biggest disasters. By calculating precise constants like the d/4 height, fiercely protecting the vulnerable knuckle from any cuts, and neutralizing stress through heat treatment, engineers can safely harness unimaginable destructive pressures inside these unassuming metal caps. Makes you wonder, doesn't it? What other high-stakes engineering battles are being fought and won inside the quiet, painted curves of the machines all around us? Next time you drive past an industrial plant, take a look at the smooth crowns capping those giant towers. You now know the intense physics hiding right there in plain sight. Thanks for tuning in to this explainer, and stay curious.